Hello everyone, welcome to the series of lectures on the course Foundations of Mathematics. In this session, I will talk about image of subsets under functions. So supposing I have a function f from the set x to the set y, and I will pick up one subset of x and let's call it a. Let a be a subset of x. Then what I'll do is I can draw a figure. Supposing this is my set x and f is a map from x to the set y, then a is a subset here, so it's here. Then I will look at all the images of points inside the set A. Okay, so if I pick up x in A, then I will look at the set f of A. I will collect all the points of the form f of x where x is coming from A. Alright, in other words, I am looking at images of all the points inside the set A. Right, so I'm looking at set of all points of the form f of x. Now these points f of x are in y because x is in the set x. So f of x, this point is in y. So I'm looking at the set of all points of the form f of x where x is coming from A. Alright, and this set is defined to be the image set of the subset A of x under the function f. Alright, then this set f of A is called image of capital A under the function small f. Alright. Alternatively, you can also define this image of A as, in other words, you can define f of A to be set of all the points in the codomain which have a pre-image inside the set E. So set of all points y in y such that there is a point here such that there exists x in x which satisfies the condition that f of x is equal to y. Same thing it means. Okay, just worded in a different way. So you collect all the points in the codomain which have a pre-image inside the set A, and that is nothing but the image of the set A under the function f. Right? So from here it's clear that this image set of A which I am talking about is a subset of the codomain y. Right? So that's image of a set under a function. Now let's look at some examples based on this, and we will try to find out image sets of some sets. So you consider a function f from R to R. For example, consider f from R to R defined by f of x equal to x square. For each x in R. Then if you take A as the singleton set, let's say 2, then what is f of A? So you are going to look at all the images of the points inside the set E, and that's a singleton set, right? So f of A is all the elements of the form f of x where x is coming from A by definition. But there is only one point in A, so that's nothing but f of 2, and f of 2 to f maps 2 to 2 square, and that's 4. So in this case, the image of this set singleton set 2 is nothing but the singleton set 4, right? If I take the set A to be this subset of R, let's say closed interval 0 comma 5, then what will be the image of this set? So I'm having all these points in my set A, then what is f of A? Each point is mapped to its square, right? So f of A will be, again by definition, set of all points of the form f of x where x is coming from A, right? In this case, you can easily see that the points in the closed interval 0, 5 will be mapped to the points in the closed interval 0, 25, because each point here will be mapped to its square, right? So this is nothing but closed interval 0, 25, right? Now what is image of an empty set? I'll state that as a remark. Image of an empty set will always be empty. Okay, so let's try to see why this is happening. If it is non-empty, then what will happen? Suppose f of empty set is not empty. If it is non-empty, then there exists a point in f of the empty set, image of the empty set. Therefore, there exists some point, let's call it B, in f of phi, that's image of the empty set. Now, when do you say that a point is there in image of a set? When there is a point in that set which is mapped to this point B. So this implies there exists a point A in the empty set such that f of A is equal to B. That's not possible because I'm getting a point in the empty set, and that's not possible because there are no points in the empty set, right? So our assumption that image of an empty set is non-empty is false, and hence we conclude that image of an empty set is always empty. All right. Next, supposing f is a function from some set x to some set y, and I'll pick up a point x in the set capital X. Supposing I have a subset A of x. Now, because x belongs to the set capital X, f of x will be inside the set y. So I have the set x here, and f maps x to the set y, and A is a subset here. So f of A will be some set here. All the image points of all the images of the points from A under the function f, those points are inside the set f of A, and x is a point in now this set capital X, such that let's assume that its image is inside the set f of A. Let's say it is here. Okay, so let f of x belong to f of A. Now, can you say that the point x belongs to the set A? can you say that the point x is there in A? So image of the point x is there in f of A. Can you guarantee that that point x which you are talking about here, whose image is there inside f of A, is there in A? The answer to this question is no. Okay, so I'll produce a counter example for this. If you look at this map, consider h from, let's say, R to R, defined by h of x is equal to, let's say, 100. Every point is mapped to 100. Then what is, and I'll pick up a set A first and let A be equal to, let's say, all the positive real numbers including 0. Then what is image of this set A? Every point is mapped to 100. So f of A will have only one point, that's 100, right? Now if you pick up a point which is not there inside the set A, choose x equal to -5, which is not there inside A. But what is f of x? That is, what is f of -5? That's 100, which is a point inside f of A. So f of -5 is there in f of A, but -5 is not there in A, right? So image of a point is there inside f of A does not mean that that point will sit inside A, not necessary. Okay, so here is a counter example for that, and you can look out for more counter examples which will tell you that if image of a point is there in f of A, then that point need not be inside A. Fine. Next, we'll see a lemma. Supposing I have a function f from the set x to the set y. Supposing this is a map, and I'll pick up two subsets of x, A and B. Let's say A and B are two subsets of x. Now if A is a subset of B, so what I have is, I have the set x here to the set y, and this is B, and A is a subset of B here. Okay, so if A is a subset of B, then we can conclude that image of A will be a subset of image of the set B. Okay, so if f of B is here, then f of A will be a set which will be a subset of f of B. So if A is a subset of B, then f of A is a subset of f of B. So let's try to prove this. We want to show that f of A is a subset of f of B. So we will start with a point in f of A. Let's say let some point y be there in f of A. So we have to show that y is there in f of B as well, right? Now because y is there in f of A, by definition y will be equal to f of x, where x is some point inside A. So y is there in f of A, that means there exists a point x in A such that f of x is equal to y, right? So we have produced a point inside the set A now, but A is a subset of B. So since A is a subset of B and x is there in A, therefore that point x must also be there inside the set B. right? Because X is a point inside the set A and A is a subset of B, correct? Now y is equal to f of x, y is equal to f of x, and x is a point inside the set B. So f of x will lie inside the set f of B, which means that y is there in f of B. So if you start with a point in f of A, then that point must also be there in f of B, and therefore we can conclude that f of A will be a subset of f of B. Okay. So if A is a subset of B, then f of A is a subset of f of B. I hope that's clear. Next, if I have two sets in the domain of the function f and I take their union. So let f from x to y be a map, and let's say a and b are two subsets of x. Then what you can say about their union, image of union of two sets. Okay, so I have my set x here, and this is set y, and some set I have here a, maybe disjoint from b, and let's see this is f of a, and let's say this is f of b. Then what will be image of union of these two sets? That is what we will see now. Okay, we will see that f of a union b is nothing but f of a union f of b. So image of union of two sets is nothing but union of their images. F of a union b is f of a union f of b. So let's prove this. We have to show that two sets are equal. So we will show that each of them is a subset of the other. Okay, so we know that A is a subset of A union B always, and B is also a subset of A union B, right? The standard result in the set theory. So if A is a subset of A union B, by the previous lemma, this implies f of A is a subset of A union B, f of A union B, and f of B will be a subset of f of A union B. Now f of A and f of B both are subsets of f of A union B. That means their union will also be a subset of f of A union B. And this implies f of A union f of B is a subset of f of A union B. So this is one side. Now we will show that f of A union f of B is a subset of f of A union B. So let's start with the point, let's say some point y in f of A union f of B. Now y is there in f of A union f of B. This means y is there in f of A or y is there in f of B. Sorry, this is not what we want. Yeah, I want to show that f of A union B is a subset of f of A union f of B, the other way. So let y be a point in f of A union B. That means y will be equal to image of some point in A union B, right? So there exists x in A union B such that f of x is equal to y, right? Now x is there in A union B, that means x is either there inside A or x is there inside B. right? Because it is there in their union. So X is either there inside the set A or it is there inside the set B. If X is there in A, then its image will be there inside f of A, right, which is a subset of f of A union f of B, and this image is nothing but Y. So Y will be there in f of A union f of B, and we are done. So we have shown that in this case f of A union B is a subset of f of A union f of B. If X is there in B, then again Y, which is equal to f of X, will be sitting inside f of B, which is a subset of f of A union f of B. So again in this case f of A union B is a subset of f of A union f of B, and hence we conclude that f of A union B is a subset of f of A union f of B. So I will mark this as 2, and now if I go back, by 1 and 2 they are equal, and hence by 1 and 2 f of A union B is nothing but f of A union f of B. Okay, so that's the conclusion. So image of union of two sets is nothing but union of their images. Now the next question that comes up is, will intersection of image of two sets be same as intersection of their images? And that is what we will see now. Okay, so supposing f is a map from X to Y, and let's say A and B are two subsets of X. Now we know that A intersection B is always a subset of A, right? So A intersection B is always a subset of A, and it is a subset of B as well. So f of A intersection B will be a subset of f of A, and f of A intersection B is a subset of f of B. So f of A intersection B is there in both f of A as well as f of B, and hence it is there in the intersection. So f of A intersection B is a subset of f of A intersection f of B, right? But what can you say about the converse? Let's try to prove the converse. That is, f of A intersection f of B is a subset of f of A intersection B. So let me start with the point in f of A intersection f of B. So let Y be a point in f of A intersection f of B. This means Y is equal to Y is there in f of A and Y is there in f of B. So this implies there exist x1 in A and x2 in B such that Y is equal to f of x1 and Y is equal to f of x2. But we wanted to show that Y is there in f of A intersection B, right? So we wanted a point X inside A intersection B such that f of X is equal to Y. Now I have a point x1 in A and x2 in B such that f of x1 is equal to Y and f of x2 is equal to Y, right? But we don't know whether the point x1 is there in A as well as B, because so far with the information that I have, I only know that x1 is there in A and x2 is there in B, right? So it may happen that x1 and x2 are two different points possibly, which are mapped to the point Y. right? So what I need is I need a point in the intersection which will be mapped to the point y. Okay, and that will happen only when f of x1 is equal to f of x2. Implies x1 is equal to x2. So from here it's clear that f of x1 is equal to f of x2. Now if I conclude that x1 is equal to x2, then because x1 is there in A, okay, if I somehow conclude that x1 is equal to x2, then I can say that I found a point inside A intersection B, because x2 is also inside B. So this point you can say, you can call it x1 now, is there in A as well as B, so it is there in the intersection. So we found a point in the intersection which is mapped to y. But this will happen only when f is 1 1. Okay, only if f is 1 1. Otherwise I cannot conclude this. That means I cannot conclude that f of A intersection f of B, that is this, the second half, is a subset of f of A intersection B, right? So I will go back now and I can put here then f of A intersection B is a subset of f of A intersection f of B. The reverse part may not be true in general, and it will be true if and only if f is 1 1. Okay, and that is what we are going to see in the next result. So the next theorem says a function f from x to y is 1 1 if and only if f of A intersection B is equal to f of A intersection f of B for all subsets A and B of x. No matter which subsets of x you pick up, f of A intersection B will be equal to f of A intersection f of B if and only if f is 1 1. First, let's assume that f is 1 1. Let f be 1 1. We will prove that this equality works. Okay. Now if you see the previous theorem, we have already proved one side, that is f of A intersection B is a subset of f of A intersection f of B. So one side is already done. So our claim is f of A intersection B is f of A intersection f of B, right? So by previous theorem we already know that f of A intersection B is a subset of f of A intersection f of B. So to prove the reverse part, let's pick up a point y in f of A intersection f of B. This means y is there in both f of A as well as f of B, right? Now because y is there in f of A, there exists a point x1 in A such that y is equal to f of x1, and because y is there in f of B, there exists a point, let me call it x2 in B, such that y is equal to f of x2. This implies f of x1 is equal to f of x2. And now because we have assumed that f is 1 1, this means x1 is equal to x2. This is since f is 1 1, right? So x1 is there in A and it is equal to x2, which is there in B. So therefore we have found a point x1 in A as well as B. That means in the set A intersection B such that f of x1 is equal to y. Therefore the point y is there in the image of the set A intersection B, and hence f of A intersection f of B is a subset of f of A intersection B. Alright, so now I can name this as star, and from star and double star I can conclude that f of A intersection B is same as f of A intersection f of B. Right, so this is by star and double star. So one side is done. Now to prove the converse, assume that f of A intersection B is equal to f of A intersection f of B, and our claim is that f is 1 1 map. Right, we need to show that f is 1 1. Now this works for all subsets A and B of X. Okay, so this trick I'll be using in this part of the proof. This works for every subsets A and B of X. So I will choose some sets A and B, and we will show that f is 1 1. Okay, so let's choose 2 points in X which are not equal. So choose x1 and x2 inside the set X such that x1 is not equal to x2. Okay, and then you form the set A to be equal to singleton set x1 and set B to be singleton set x2. Now because x1 and x2 are not equal, A intersection B is definitely empty, right? A intersection B is empty because x1 is not equal to x2. Then what is f of x1 intersection f of x2? Let's look at this. Then if I look at this set f of x1, this is a set now, intersection f of x2. Okay, what will be intersection of these two sets? Yes, now that's correct. So A contains only single point x1, so f of x1 is nothing but f of A, and f of x2 is nothing but f of B. So this is f of A intersection f of B. But by our assumption, f of A intersection f of B is f of A intersection B, and because A intersection B is empty, this is f of empty set, and that's empty. That means this set f of x1 intersection f of f2, intersection of these two sets is empty, and therefore f of x1 cannot be same as f of x2. So what we showed is if x1 is not equal to x2, then f of x1 is not equal to f of x2, and hence f is 1 1. So this proves the second part of the result, and hence we conclude that a map f is 1 1 if and only if this property works, that is f of A intersection B is equal to f of A intersection f of B for every subset of X. Okay, yeah, so that's it for this session, and I will continue this section in the next video. These are my references. Thank you.